Hello, this video will help you with problem 23 in chapter 4. Um, in this case, I'm actually going to draw the diagram that they gave you. You're not only going to draw that, but I'm drawing it just because I don't like the way they did it, and I'm going to explain why. So they have a rope basically like this, and they show a person's foot here and here. And then basically they have the person like that. I'm going to do it again anyway, so it doesn't matter. But they show it as though this part just keeps coming down at an angle, okay? Which wouldn't happen if the feet are here and here. The rope would look like this. And then the foot part, and then up like that. If the foot's here and here, this part would be spread. This part would be, this part right here would be flat between the 2 feet, okay? So we're not going to draw it the way they do it because although they are assuming the problem looks like that, they didn't draw the feet correctly. Is that the middle? Let me redraw this. 2, 3, 4, 5. There. 1, 2, 3, 4, 5. That's weird. Yeah, whatever. It's close enough. So I'm going to put the feet closer like this. And we have the person. And the person was holding a stick for balance. So you have a stick like that. And like that. And then you have the person walking around. And you're going to have the point right here treated as the center of mass. That point I put there in red. Now we're going to draw a free body diagram. Now if you went straight to this, that's fine. Okay, that's what you're supposed to do. I'm just explaining why the drawing is not the best. So we have the force of gravity going down. You have, oops, that should have been straighter. There you go. You have a force of tension going like this. A force of tension going like this. The angle here and here is 10 degrees. Theta is 10 degrees. I labeled them both as theta because they're the same value. And then the mass is 50 kilograms. And we can know that obviously the force of gravity is the mass times the acceleration due to gravity. We're trying to find the force of tension. So it's important to realize that the person is in mechanical equilibrium standing on that string right there, okay? Which means that the forces in the x direction and the forces in the y direction have to cancel. And we actually don't care about the x direction in this case. We can solve the whole thing just looking at the y. Just go ahead and do that then. So some of the forces in the y will equal ft sine of 10 degrees. Okay, so that's one component of the rope. Now keep this in mind. There's a rope to the right and a rope to the left. It's the same rope, that's true, but there's 2 forces of tension there. So you actually have to add it twice. Force of tension times the sine of 10 degrees a second time. Okay? And then you have to subtract the force of gravity. Now we know that the sum of the forces will be 0 in this case. So you have 2ft sine of 10 degrees will equal fg. We can divide it by 2 sine of 10 degrees. You have ft equals fg over 2 sine of 10 degrees. So ft will equal 50 kilograms times 9.8 meters per second squared. Remember, that's just mg. I already wrote that earlier. Divided by 2 times the sine of 10 degrees. So Ft will equal 1,410 newtons. With scientific notation and significant figures, you should have that the force of tension will equal, you know what I realized? They gave you 50.0 and 10.0, so it's 3 sig figs. I didn't write it down all the way through, so it's 1.41 times 10 to the third newtons. Okay. Zoom out. So other than a poorly drawn diagram that they give you from the book, it should be easy to know that you have that force in the center mass in the middle there, and we can account for all the forces that go from tension to ropes. I think that's probably the most common mistake, is thinking that there's only one rope, but it's on both sides, so the tension is there for both components. Keep this in mind. The force of tension, if it was just one part, that would be like a person swinging on a vine. Because if I cut the rope at the person's foot to the right, then we know the person's just going to swing and smash in to that part over there. If you cut this side right here, okay, so that means that this component of the rope has to be holding this part of the rope. They work together. So just keep that in mind.